Good evening and welcome to Chabot Space and Science Center's Friday virtual program, Planetary Defense, Avoiding Cosmic Catastrophe. My name is Lisa Hoover and I'll be your host this evening. We are so pleased to be hosting this event with our longtime partner, the Lawrence Livermore National Laboratory. Tonight, our guest speakers are Dr. Megan Bruck Syal and Dr. Mary Burkey. About Dr. Megan Bruck Syal. She's a group leader in the Design Physics Division at Lawrence Livermore National Laboratory, where she leads the Planetary Defense Project. She has a PhD in planetary geosciences and a master's in engineering from Brown University, where she investigated asteroid, comet impacts and using experiments with computer simulations. She uses a variety of numerical methods and experimental platforms to understand material response to energy disposition and shock. Dr. Mary Burkey is currently a postdoctoral scholar at the Lawrence Livermore National Labs in the Planetary Defense Group, where she works on modeling the nuclear deflection of asteroids. Before coming to the laboratory, she was a Marzan Fellow at the National Academies of Science for the Committee on International Security Arms Control. She earned her PhD in nuclear physics at the University of Chicago and Argonne National Laboratory. At the end of their presentation, we'll have a brief question and answer period, so cook up some good ones, and I'll see you back real soon. Without further ado, I'm going to turn it over to Dr. Megan.
All right, well, thank you so much for that great introduction. We're really pleased to be chatting with you tonight about our research on planetary defense. I think we're gonna go to the next slide. Great. So planetary defense is a relatively new field of study, which seeks to answer an important question. If an asteroid or a comet were going to possibly impact the Earth, what could we do to prevent it? And at Lawrence Livermore, we've had the opportunity to think quite a bit about this question and do a lot of research on what our options would be. So we're going to be talking about that here tonight. Now, this is what most people might think of when they think of asteroid threats and how damaging they can be, the impact that it took out the dinosaurs 65 million years ago. And this was a really bad day for the dinosaurs and for the other 3/4 of plant and animal life that were wiped out by this event. And it's important to recognize that this was a very large asteroid. It was 10 kilometers in diameter or so, something like the size of the city of San Francisco. And as we'll find out as we step through the talk, it's not really that size of asteroid that we're worried about today so much. It's not these globally devastating impacts that would cause an extinction level event to occur, but it's really things that are in the medium asteroid size range that we're worried about. So what happens if we go back, that was 65 million years ago. When we go back a little bit more recent history, this is 50,000 years ago in northern Arizona, a really well-preserved impact crater called Meteor Crater, appropriately. Meteor Crater is really special because it was the first widely recognized crater that was caused by an asteroid, the first extraterrestrial cause of a crater here on Earth. And it was only in that late 50s, really, that there was that broad recognition amongst the scientific community. And I really recommend, if you have an opportunity, to take a road trip to go visit Meteor Crater. It's about halfway between Flagstaff and Winslow in northern Arizona. And it's just beautiful. It's breathtaking. And I think it's really a cool thing to go visit. You can see the visitor center on the right-hand side there for scale. It's a little over 1 kilometer in diameter. And I think it's amazing to think about the thing that caused this was not very big at all. It was only 50 meters across. It was an iron nickel asteroid, so relatively high density asteroid, which makes it more effective at excavating a big crater. So asteroids can come in a variety of compositions. Some of the most dangerous ones would be that high density metal, the metal asteroids that have this iron nickel composition, but a lot of asteroids are rocky as well. And this is a really good example as we go into a more recent time, just 7 years ago in Chelyabinsk, Russia, there was something that really wasn't that big, only 17 meters across. And for things that small, we typically, they're very difficult to detect. Astronomers have a really tough time still detecting things this small. And so this one came out of nowhere. No one predicted it was going to impact the Earth and took a lot of people by surprise. This was in February 2013. And in Russia, a lot of people have cameras on their dashboards of their cars. So there's a lot of videos and images like this one capturing those moments, which had to be really scary. And luckily, no one was killed by this event. It deposited about 500 kilotons of energy in the atmosphere. So that's a whole lot of energy. You know, that's something like 50 times larger than an atomic bomb explosion. And it mostly just blew out windows, and most of the injuries associated with it were caused by broken glass from windows. However, and this was a rocky asteroid, so as it deposited most of its energy in the atmosphere, it slowed down. So by the time the solid pieces got to the Earth, they were moving much more slowly, and most of them landed in a frozen pond, and they're able to recover some of the fragments from that. But we don't have to go up much larger in size from this for it to be really damaging. So the Tunguska event in 1908 also occurred over Russia in a very thinly populated region. I don't think there are hardly any people living there at that time. And it flattened about 2,000 square kilometers of forest. And to visualize that, it's about the area of the Washington, D.C. metro area. So if that happened over an urban region, it would be really devastating. There'd be a lot of loss of life. And that rocky asteroid was only about 70 meters across. So you don't have to go much bigger for these events to be really dangerous. And there's a lot of asteroids in that size range that are still not well characterized, not discovered by telescopes yet. If you look up at the moon, and especially if you take a good pair of binoculars, it's really incredible how well preserved the impact craters are on that surface. It's an airless body, so there's not the atmosphere. There's also not tectonic recycling, vegetation, all the things that contribute on Earth to hiding Earth's scars from the past, from its past bombardment history. So it's only relatively recently that scientists have recognized that Earth has gotten pummeled by a lot of asteroid impacts in the past. And so this map highlights all of the major impact events that have been discovered. And it's exaggerated a little bit. So the circles are they're to scale with the size of the crater. So at the far low end of the scale, an example might be meteor crater, which also appears as red because it's one of the youngest craters on this map. So it's color coded by red is less than 1 million years old. So meteor crater at 50,000 is well within that cutoff. And then something a little bit older like Chicxulub, which was the impact that took out the dinosaurs. That's the name that scientists give that impact. It's also called the KT boundary extinction event. Now you can see that occurred in the Yucatan Peninsula area in Mexico. That's in the 10 to 100 million year range, that's colored green. And then some of the oldest craters, for example, here are colored gray. So Vredefort in South Africa is a gray one. It's older than 1 billion years old. And a lot of work has to go into discovering some of these. Sometimes it's very complicated geophysical analyses that help scientists uncover where impact craters were. or also geochemical analyses looking for signatures of the very high pressures and temperatures that are associated with the meteor impact, and it can cause very remarkable shock features that they look for to positively identify something as a previous impact from an asteroid or a comet. And we're getting hit all the time by lots of little things. So lots of little bits of comets and asteroids are hitting Earth, and they're visible to us as meteors or what we would call shooting stars, where they're just getting bright as they heat up in the atmosphere, but they don't get down to the Earth's surface. Then they just put on a nice show. And here's a time-lapse image, for example, of the Perseid meteor shower from August 2009, where they took an image and looked at a lot of meteors over time, looking at their tails and capturing that. So there's lots of bits and pieces that Earth is always getting hit with. But it's the slightly bigger things, of course, that we're worried about. And so this is a really nice video that the folks at NASA JPL put together, looking at how our understanding of the near-Earth object population has changed over the last 20 years. And before we start the video, I'll just try to orient you. So right now there's about 2,000 near-Earth asteroids discovered every year. And at the center of this is the sun, of course. Earth's orbit is shown in the gray circle, and Mars' orbit a little bit outside that is that red circle. And then in between Mars and Jupiter would be where the asteroid belt is. And that's where most asteroids reside. And they're not a threat to Earth there. They're not on orbits that would intersect with the Earth's orbit. It's only when asteroids are perturbed from the asteroid belt, either by Jupiter's gravity or impacts or the absorption or irradiation of light in a way over time that delivers some momentum sometimes, then they can get perturbed into orbits that could be dangerous for us on Earth. And so Jupiter's orbit at the very edge of this frame is shown in yellow. So we're gonna step through this video. Now you can see all the little teal dots show near Earth objects that were identified in 1999. 10 years later, quite a few more of these near-Earth asteroids, and then another 9 years later, even more of these near-Earth asteroids. And now we're filling in with the asteroid belt asteroids in brown there. And the threat looks a little bit scarier than it really is, because each pixel here is bigger than the asteroid would be in space on a solar system spatial scale. So it looks denser than it actually is in real life. But it does give a sense of how many asteroids there are that could be a threat to Earth, and what a huge job it is for astronomers to track all of these asteroids accurately. How do we see them? Well, if you think about the electromagnetic spectrum, so light comes in a variety of wavelengths, and the wavelengths that humans see in are a relatively small part of that. In between, on this shown here schematically, in between ultraviolet and infrared, there's a narrow band where humans can see. And there are a lot of telescopes that look in that part of the spectrum too. So the Pan-STARRS telescope in Hawaii is a really good example of something that's a workhorse for discovering asteroids and doing follow-up observations to make sure that we understand their orbits really well. Catalina Sky Survey in southern Arizona is another workhorse observatory that discovers a lot of near-Earth asteroids. If you go to a little bit longer wavelengths in the infrared, the NEOSM mission it stands for Near-Earth Object Surveillance Mission, is something that if it was to be fully approved, now it's gotten good community support, but hasn't been fully approved by Congress to be flown. It would be fully dedicated to hunting down asteroids. It'd be a space-based observatory in orbit around Earth that was just hunting asteroids all the time. And that would be really helpful for discovering some of those smaller asteroids where our gaps in knowledge are still a big problem. And so I'm really hopeful. I think all of us that work in planetary defense are really hopeful that mission will come to fruition in the near future. It's based out of the University of Arizona. And infrared's a really good place to look at asteroids because of their temperatures. They're relatively cool. They radiate most of their heat in the infrared part of the spectrum. So you can learn more about their composition and how reflective they are, which is important for getting better size estimates. If you go to longer wavelengths, the radio wave part of the spectrum, Arecibo telescope in Puerto Rico, very iconic giant dish you've probably seen pictures of before. That's a really important facility for getting really detailed shape information on asteroids. So often when they know an asteroid is going to have a close approach to Earth, they can look at it with Arecibo and develop something like this image you see here, where it looks almost like a skull shape there. And that asteroid was discovered near Halloween a few years ago, and they nicknamed him Spooky. And every once in a while, we're really lucky to get an up-close view of an asteroid. So when they're first discovered, they just look like a few pixels on a CCD image. But if you send a space mission to an asteroid, such as the OSIRIS-REx mission, it's currently in orbit around asteroid Bennu, shown here, then you get this wonderful view of the incredible structures that exist on asteroids. You can see it's got this very rubble pile type structure. The asteroids are very collisionally processed. They've experienced a lot of impacts, whether it's within the asteroid belt or afterwards. They've been pummeled into a lot of different pieces of different sizes. And so it looks like a grab bag of different boulder sizes and pebbles and smaller grains. And Bennu is about 500 meters in diameter. To give you an idea, that's about the height of the Sears Tower, so a really big skyscraper. And Bennu is a really interesting object because it comes really close to the Earth every 6 years. And so it was pretty well characterized by radar and a variety of telescopes before they even visited it. And we've used Bennu in the past in our research group as a really good case study for a near-Earth object. If it were going to threaten the Earth, how we would prevent it from impacting. Because in the future, it does have a very small chance of impacting Earth. It's, I think it's 1 in 2,200 or something, 1 in 2,700 chance of impacting Earth late next century. So it's not something to lose sleep over, but it is a good test case of our modeling capabilities to see how we could prevent something from Bennu impacting. And another point I wanted to make is that these asteroids, when we think of their what context they're in with the greater solar system, they're the leftovers from planet formation. So when early in our solar system's history, material accreted into the terrestrial planets, but a lot of smaller bits and pieces were left over, and those became what we know today as the asteroids. This table helps give a sense of, for each different size range of asteroids, how many we think are out there, how many have been well observed, and what kind of destruction they could cause. So at the large end of the spectrum, there's things that are 1 kilometer or 10 to 10 kilometers in diameter. So that's the size of a mountain like Mount Whitney, the biggest mountain in California. There's only about 2,000 of those out there, we think, and scientists have a pretty good handle on those. Probably around 94% of them have been observed and their orbits are well characterized. They're not going to be a threat to us anytime soon. And that's good news, because we know that there would be global effects from an impact that size. If we look at the lower end of the spectrum at 1 to 10 meters in diameter, that's about the size of a bus. There's more than 500 million of those out there. And a very, very small percentage of those have been observed, but those are small enough that they don't really pose a threat. They're really on the scale where they're causing a meteor shower event. It's just a nice light show in the sky. Nothing gets down to the Earth. It's really in this center region between 100 meters to 1,000 meters, where there's about 130,000 of those out there. We've only really observed probably 18% of those. Those could still cause regional catastrophe, and that's why telescopes like NEOSM are really important to get out there and get looking for things in that size range. And if you go a little bit smaller than that, 10 to 100 meters, there's many more of those, 10 million. Probably only 0.5% of those have been observed. And some of those can also be really dangerous. So Tunguska in 1908, that was in that size range, 70 meters or so. And that would be really bad if it occurred over a city. So there's still a lot of work to be done in discovering these asteroids. The US government has a long-standing interest in the asteroid threat and what we can do to be ready. And more recently, there's been a lot of effort to develop a clear action plan. So in 2018, the White House's Office of Science and Technology Policy released a near-Earth object strategy, preparedness strategy and action plan, which that had been worked on for a few years before that. And a lot of experts provided input to how to make it work well. And the idea is to provide a 10-year roadmap for all the different agencies and departments in the federal government to work constructively together to be better prepared to handle future threats. And they divide it into 5 goals. The first, of course, is finding asteroids. So you have to find them before you can be ready to defend against them. The second is where our group comes in a lot, is computer simulations. And Mary will talk more about that in a minute, about how we simulate asteroid response to various deflection techniques. The third goal involves mission technology. And a really good example of this is NASA's DART mission, Double Asteroid Redirect Test. It'll be the first ever test of an asteroid deflection. That's occurring in 2022. It's going to launch next year in 2021. And our group has been involved with the DART mission for over 5 years now. And it's really an incredible opportunity to test how effective our deflection technologies can be. And there's a lot of other missions in development that are going to be hopefully advancing our understanding of asteroids. The next component is international cooperation. Planetary defense is a very global problem. Obviously, it could affect any country, and the spacefaring nations like the US bear an extra responsibility to be prepared. But we need to partner with folks from around the world so we're ready to go through all of the decision-making processes that would happen in a real event. And so we practice this regularly at planetary defense conferences, which occur every 2 years. And the last is emergency procedures. So sometimes an asteroid might be heading toward the Earth and there's not time to prevent it from impacting, but we still want to be able to provide a very detailed consequence assessment prediction, hand it off to the right people at FEMA within the Department of Homeland Security so that they can advise evacuations, how to secure infrastructure. And so there's a lot of work that goes into that, and our group also contributes in that area as well. So now I'm going to hand off to my colleague, Mary, who's going to be talking about what can we do if an asteroid is going to impact the Earth.
All right, thanks, Megan. Everyone can see and hear me okay, hopefully. All right, great. So Megan did an excellent job about walking us through the threat and how we're getting ready for the threat. So now we have a plan to make a plan, but now I'm going to tell you what the plan might actually look like if there was indeed an asteroid heading to Earth. So here's a cartoon of example. We have Earth on the blue trajectory and an asteroid incoming on the red one, and they're due to collide. So now the question becomes, what can we do to save ourselves? So there are a few different options, various technologies that we are exploring, and like Megan said, we at Lawrence Livermore do a lot of work to try and help figure out as much of the information as possible about all of these different mission types. So I'm going to walk you through a few different options. This is our favorite one. It's called a kinetic impactor. It's our most developed technology, and Megan mentioned a couple of times with the DART mission. But the basic idea is if we see an asteroid a few decades in advance and it's coming to Earth, we can run over to our friends at SpaceX, ask very nicely to borrow a spaceship, load a spacecraft onto that spaceship, launch it into space, give the people at SpaceX back their rocket, just in case we need it later, fly our little spacecraft over to the asteroid and crash it into the asteroid, with the intent being just to nudge it just a little bit and change the velocity of the asteroid by about 1 centimeter a second. And if we have a decade of warning time, that's enough for the asteroid to be able to change its velocity and change its trajectory so it can miss the Earth. So that may not seem very much, but over in a decade, it's quite a lot, and it can make a difference. So that's our first option. So it might seem very simple, but there's a lot of questions that go around since we can only really send up one test mission, and not very many over decades. There's not really a test run after this if an asteroid were to come. So the best thing that we can do instead is to run lots of simulations to try and answer as many questions about how the collision is going to go and how much velocity is going to be imparted beforehand. And how you do that is with really, really, really big computers. But luckily, Lawrence Livermore National Lab has some of the most powerful supercomputers in the world. We just welcomed another one online about a couple of years ago, and I think it's second in the world right now in terms of supercomputers. And it has about 1,380 terabytes worth of processing power and about 200,000 cores. So it takes up quite a lot of electricity in rooms and space, but it is immensely powerful. So this one probably wasn't run on Sierra since it's a very simplified version, but this is an example of some kind of an approximation simulation that we might run to see what a kinetic impactor might actually look like. For instance, say if you didn't actually hit it on the nose of the asteroid, but instead hit it kind of at an angle. So the colored bits of ejecta that are flying off of it are ones that are flying in the opposite direction of where you hit it or where you want the asteroid to go. And they're giving you an extra push of momentum and kind of leading it, you get an extra boost. However, all of the gray material is moving in the same direction as the asteroid and therefore hindering that boost that all of the colored ejecta have given you. So knowing those kinds of things, because you're not going to exactly have an idea of what angle you're going to hit at the asteroid. So that's going to add some extra error to your calculations when you're figuring out the deflection velocity. So good things to know. Of course, a very nice smooth ellipsoid is not really what asteroids look like. They tend to look a bit more like this one on the left, which was taken by the Japanese Hayabusa mission. It's called Itokawa, and it looks a bit kind of like an awkward nose. But as you can see, as Megan mentioned before with Bennu, it's got lots of different sized boulders. They're all distributed kind of in weird ways, and you can even see maybe some kind of like matrix material or kind of sand-ish smooth material along the top and bottom. So that behaves much differently than just a traditional ellipsoid that is the same throughout. So we try to fold that extra structure into our simulations. And the example of that would be on the right, where we still have the ellipsoid, but then we have an ellipsoid with boulders and matrix material as well. And you can see an example of our little spacecraft at the top for comparison that's about to crash into the top of the asteroid. And so we'll be able to simulate that. Of course, those kinds of simulations are very expensive. So the idea usually is to make the place where the little spacecraft is going to hit the highest resolution so you can catch the shock wave, and then you can decrease the resolution as you go towards the bottom of the asteroid where it may not make such a big difference. So we've mentioned DART a couple of times, but now it's very exciting for us. So now we're going to talk about it in a little bit more detail. So the basic idea is we're going to do exactly what was in those cartoons a couple slides before. We're going to send out a spacecraft and we're going to crash it into this little asteroid over here. And it's going to release some ejecta, and it's going to change the trajectory of the asteroid, compounded with the momentum from the actual spacecraft. And the reason and the point of this is to eventually measure what actually the difference in trajectory is of this little asteroid right here. So we're aiming for a binary asteroid system called Didymos, and we're hoping to hit this little asteroid that's rotating it called, it was nicknamed Didymoon for a while, but now it has been officially named Dimorphos, so it's having a bit of an identity crisis. But the idea is if we hit this tiny asteroid while it's rotating around the bigger one, we will actually be able to see the difference in orbit from Earth. And from there, we can tell exactly, we can try and see how successful this test was, like how effective were we. So the launch date is due on July 22nd of 2021. SpaceX is kindly offered to bring it into space for us. So weather permitting on July 22nd, we should be good to go. And we're hoping for an impact date in October of 2022. However, there are some instances where kinetic impactors won't work. There may be, it may be that the asteroid is perhaps too small. You might break it apart if you try to hit it, or it might be too big for you to be able to impart enough momentum, or you might just not have enough time to give it that 1 centimeter a second deflection to make a difference. So here is our second option if that isn't available. So as I mentioned, so you can only launch so much mass off of Earth. It's very expensive and tricky to do this still. So whatever you launch, you want to make it count if the fate of the Earth is in the balance. So you want, I guess, as much energy as you can possibly get to impart to this asteroid on your rocket. So over here on the right is a chart. If you were to say to launch as much TNT on your rocket as you could possibly get, your energy output would be about 6 megajoules per kilogram of weight. So if you did want to send up some TNT, that probably wouldn't be the best option. For comparison, a kinetic impactor, if you can get it going about 10 kilometers a second, which isn't difficult to do in the vacuum of space, you're talking about 50 megajoules per kilogram of energy output that you can fit on your rocket. But if that's not enough, you have to look at your next option, which for scale is the other 2 bars have been lowered. So if you were to load a nuclear device onto your rocket and send that to the asteroid, you're looking at about 4 million megajoules per kilogram. So this is about literally as much bang for your buck as you can possibly have. So the next option is to use a nuclear device. And it works to a point pretty similar to the kinetic impactor. You go back to SpaceX and you borrow the rocket, you launch you put your spacecraft on the rocket and you launch it into space. You give SpaceX back their rocket in case we need it later. You fly your spacecraft over to the asteroid. And there's actually 2 different options inside the nuclear option. The first of which is nuclear deflection, which is similar to a kinetic impactor in that you want to keep the asteroid intact while you give it a push. So the idea is you'll kind of keep your spacecraft a little bit at a standoff distance from your asteroid, and you'll detonate it there. And you'll be able to illuminate, it'll give off a lot of X-rays and a few neutrons, and those will propagate over to the asteroid and they'll heat up the surface. And the idea is they'll heat up just enough surface material that it will melt and it'll vaporize and it'll expand rapidly and it'll be ejected from the surface of the asteroid. And that ejecta in the opposite direction will give the asteroid a push in the forward direction, which will ideally be enough to have it miss the Earth. So that's great. But of course, just because you send up the most powerful thing doesn't mean that it works as you want it all the time. There's still lots of questions to be answered. So like, for instance, as Megan had mentioned before, we don't always know what asteroids are made out of. They could be made of rocks, but who knows what kinds of rocks. They could be made out of metal, but how much metal? So we can look at asteroid samples on Earth, but those are the only ones that have made it through the atmosphere. So there's a bit of a sampling bias. So but what kind of material you're actually working with matters in terms of what the energy from the nuclear device does. So that's a serious question. Another one is like, what's the structure of the asteroid? Does it have like a really, really dense core that all of this other rubble is kind of forming around, or is it just kind of like a loose band of rocks? So that makes a difference too, and that's not always easy to see when you're, especially if you're just looking at a bright dot, and that's all the data on your asteroid that you have. Another is shape. Not all the asteroids look like as kind of spherical as Bennu does. They can look like the nose, like Itokawa, or they can look at like this rubber ducky over here. And then you might have some shadow when your nuclear device, the X-rays, are illuminating the surface of the asteroid. So that would make a difference in your deflection velocity as well. So for those kinds of questions, at least for the composition one, we can do simulations like these, where we apply a bunch of what we think the energy from a nuclear device might look like to the surface of a very simplified asteroid, one made of pure metal and one made of stone, and we can see what the ablation might look like. So the simulations here are showing the temperature of the ejected material, and you can see that the pure metal is substantially hotter because it's denser, and the X-rays won't be able to penetrate as deeply. So you'll just have a whole lot of energy just on the surface, but not very deep. So just the top heats up and goes off very quickly, but it'll actually, in the long run, it's a bit deceptive because it ends up being less mass because the X-rays weren't able to penetrate quite as deeply as the stone. So the ejected takes a little longer in the stone's case, but you get more of it and therefore more of a boost. So, but the second option is probably the option that you're a little bit more familiar with from various Hollywood impressions. And this is the case where you, instead of trying to keep the asteroid together and just push it, you want to, if it's going to fall apart, or if you want it to fall apart, you want to blow it up with feeling. So this is where you bring your nuclear device as close to the asteroid as you feel you can get it. And you detonate it, and all of the X-rays and neutrons hit the smaller surface of the asteroid, and that creates a shock wave that will propagate through the entire asteroid and theoretically blow it to bits. And that's called nuclear disruption. So, and if you can do that usually at least a month in advance, all of your smaller fragments that you've created will have enough velocity that they will also hit the Earth, or they will also not hit the Earth. So that would also be considered a day saved. But again, it's not always quite that simple. Even if you are trying to blow it to bits, you do want to do your homework and do the simulation to make sure that you are going to get exactly what you expect. So over here, being simulated is a Bennu type asteroid with a 1 megaton source being detonated right at the surface. And you can see the fragments now being sped up as they fly off, and you can see the shock wave penetrating into the asteroid. So on the left is a close-up of what that might look like with another part of the simulation that's also very important when looking at a nuclear disruption, and that's fragment tracking. So once you've actually blown up your asteroid, you now have a lot of very tiny asteroids, and it may be worth your time to give those to another simulation that tracks the gravity and body physics. So you can keep track of what all of your fragments are doing, and you can tell the policymakers, yes, I blew up the asteroid, but I've kept track of all the fragments and none of them are going to hit Earth in the next few years. And that's usually generally appreciated. So I've given you several options. Now the question is, which option is best? This will obviously be up to the people in charge at the time whenever such a crisis would occur, but generally speaking, we can give them a bit of guidance on which ones will probably do the best jobs under which circumstances. The two biggest questions being, how big is the asteroid and how much time do we have? As I mentioned before, for a kinetic impactor, you generally want a couple of decades worth of notice so you can give it that little bit of a push over time. And that will generally work for asteroids, maybe up to about 200 to 300 meters. But anything bigger than that, even with decades of notice, we may not have enough oomph to get a kinetic impactor big enough for those bigger asteroids up into space. And at that point, we may want to use a nuclear device instead to deflect it. And if we start getting closer and closer to the day, say maybe we only have years or months, and the asteroid is maybe a bit on the smaller side, we may want to go towards a nuclear disruption route. Because if you try to give it too big of a push while keeping it intact, you may, in fact, push it too hard and break it apart. And then you have a whole bunch of small fragments heading towards Earth, which is not exactly ideal either. So at that point, you would want to blow it up with feeling. And of course, the final option, which you've probably already noticed in red, is if it is too late or if it's too big, the only thing we have left to do is brace for impact. However, there is still a place for simulation modeling in that respect as well. So for instance, we mentioned the Chelyabinsk event, which was called an airburst event, where the asteroid entered the atmosphere and it essentially blew up. You would want to know what it would do in advance. So we have people at the lab who simulate things like that. So here's a simulation of an asteroid entering the atmosphere and breaking it apart and depositing its energy. The point of this simulation was to compare between this one, which you started out with a kind of a sphere that had a bit of a rough surface, and compare that to what physicists usually like to use, which is just a perfect sphere. And though that video, just the perfect sphere isn't here, it was very different than the more realistic one shown here. So details do matter. The other thing that we might look at is, say, Earth is covered, as you may have noticed, with quite a bit of water. And we as humans very much like the coast, and we like to build our population centers next to it. But if, say, an asteroid were to hit the water close to one of these population centers, you could have a pretty serious problem, i.e. a massive wave. And so we also have people who would say, look at an asteroid entering the water and creating a shock wave. And then they can pass that data off to another a wave propagation code. And over here, you can see on the right is that, say, this shock water column being propagated from a point in the Japan Sea. And the colors that you can see on the right are how high or how low the waves are, and where those waves might hit along Japan's coast. So also very useful. This is another example of, say, an asteroid hitting the Gulf of Mexico. But this is atmospheric modeling. So if something really hot and fast moving enters the water, a whole lot of water is in turn going to be ejected into the atmosphere and potentially vaporized. And seawater isn't just pure water, there's lots of other stuff in it. In this case, the simulation is looking at hydrochloric acid being circulated around the atmosphere over the course of a couple of weeks. Hydrochloric acid in particular has a very nice habit of depleting ozone. So if you're fair-skinned like me and we happen to be hit by an asteroid and there's a similar plume to this, you may want to stay inside a bit more or wear a hat or lots of sunscreen, amongst other things. I'm sure there'll be many more problems besides that. So this is watching how the plume would circulate around the global atmosphere. So So that is everything that we do at Lawrence Livermore National Lab. We live in the Department of Energy, and our lab is specifically watched over by the National Nuclear Security Administration, which is a branch of the Department of Energy. But we also have colleagues, especially for the emergency part or the emergency response part of the planetary defense at U.S. Department of Homeland Security, which oversees the Federal Emergency Management Agency. And so all of us work together, along with our colleagues at NASA, to help defend the Earth and the US from asteroids. And all of us are overseen by the Planetary Defense Coordination Office, which was stood up in 2016. And they have t-shirts if you're interested. And they keep us all honest and working hard and keeping them updated of all the progress that we are making. And since, of course, deadly space rocks is very much a global enemy, we have many friends working internationally. As Megan mentioned, there's a planetary defense conference every 2 years. So here's a picture of the one from 2015, and all of the countries that were represented and their flags are seen there. It was quite a big party, and much research was discussed. So that is all of our action plan, all of the aspects of our action plan. I think we've covered finding asteroids, simulating them, mission technology, international cooperation, and emergency procedures. So with that, I will show you, this is all of our amazing colleagues at Lawrence Livermore. It's not just me and Megan working hard to keep you safe. We have all of these wonderful people working alongside us on all of the different problems that I just shown. And with that, I will conclude. Are there any questions? I think I've seen a couple pop up on the chat.
Wow, that was amazing. Thank you so much. We have a lot of questions, so we will get through as many as we can. Starting with, did the Russian meteor explode at a high altitude, thereby reducing the force reaching the city?
Yes, yeah, it was I don't remember the exact height. I would have to look up how many kilometers it was at which it deposited most of its energy. So it starts burning up as it comes into the atmosphere. And then there's typically one height at which there's a big explosion and most of the energy is deposited. And I don't remember off the top of my head where that was, but depending on the asteroid's composition and also the angle at which it's coming in and how big it is, that will change the height at which it deposits most of its energy. So something a little bit bigger, a little bit higher density, or even a little bit a steeper angle might have gotten farther down into the atmosphere before exploding and done more damage.
Awesome. Here's another one. Is the International Space Station being hit with small meteorites?
Yeah, that's a really good question. Yes, almost certainly there's small bits of dust that encounter everything that's in orbit around the Earth, and most things for that reason, going way back to the dawn of the space age, are equipped with shielding to protect them from those small impacts that, even though they're mostly very small, because they're traveling at hypervelocities, so many kilometers per second, they can do a lot of damage potentially. So typically everything that's in space has some shielding to accommodate those impacts of little things that are hitting them.
Thank you. Here's a question from one of our 7-year-old guests. Do asteroids ever leave toxic chemicals behind when they land on Earth?
Oh, that's an interesting one. I'm not 100% sure, but I don't know of a lot of toxic chemicals associated with asteroid impacts. Yeah, it's relatively recent that that scientists have been able to track small meteors before they impact, and then go and hunt for them after they've impacted. So there's a few examples of when that's happened recently, because it's so hard to track the really small things. And most of what's hitting us on a regular basis is small like that. And I don't think there's toxic things associated with it, but I'm not 100% sure.
Great question. Is the Earth's moon being hit as well as, and are there instruments on the moon to detect these impacts?
That's a really great question. Yes, I believe going back to the Apollo era, they installed seismometers at the moon, which were capable of detecting small impacts. And so there is some data on the impact frequency at the moon through that. The other way that we track impacts at the moon over time is looking at lunar flashes. So there's certain telescopes that have looked at the moon for long periods of time, hunting for any flash that might occur. And based on the luminosity, how bright that flash is, they can develop an estimate of how large it is, what velocity. Sometimes you have additional information about that's associated with a meteor shower. So you know that it's a time of the year where there's a lot of things that are coming from bits and pieces of a comet and then you have a better idea of what angle it came from. And so, yes. And also the other thing they can track on the moon is cameras like the Lunar Reconnaissance Orbiter mission. The LRO has a camera called LROC, Lunar Reconnaissance Orbiter camera, which took a lot of really high resolution images of the moon over a long period of time. And sometimes you'll discover a new impact because between an image on one day and an image a few days later in the same place, there was a crater formed, which is really interesting. And it helps scientists develop a better understanding of the impact flux today at the moon, which actually is our best calibration for the impact flux today at Earth, because the moon preserves impact craters so beautifully.
Here's another one. Does the recent increase in low Earth orbit communication satellites reduce the effectiveness of locating asteroids?
Oh, that's interesting. You know, the addition of more low Earth orbit satellites is an issue for a lot of astronomers, particularly amateur astronomers, and being able to study various objects that they would be interested in. A lot of the professional observatories, my understanding is they can typically work around that because it's a little bit easier for them to plan ahead of where those satellites will be and look accordingly. But it could potentially be an issue, I think. But yeah, that's a really good question. I think I'm definitely not an expert in observational astronomy of asteroids, so I'd be interested what an expert would say on that too.
All right. Here's another question. Which spectrum would you look in the infrared spectrum? And there's a couple listed here: SWIR, CHIR, etc.
Yeah, that's a good question. For those not familiar, I think those acronyms, so SWIR would be short wavelength infrared, and then MW would be for mid wavelength infrared, and then LW, long wavelength infrared, and depending on what definition you use for the cutoff between them, I think for the NEOSM mission, which we talked about, would be a space-based observatory that just is fully dedicated to hunting down asteroids. It would have infrared, it'd be looking in the infrared region between 4 and 10, or 4 and 10-ish microns. So that's kind of in the, I guess, the mid-range, mid-wavelength infrared range or thermal infrared range. A lot of where planetary scientists like to look at asteroids to learn more about their origins, and particularly their ability to host water, is within near the 3 micron wavelength range. There's a lot of characteristic absorptions for water molecules in that range. And so depending on what you're interested in, planetary scientists look in different parts of the infrared spectrum.
Great. Here's another question. Can the behavior of an asteroid change, like changing its orbit?
Yes. So the behavior, sorry, the question was the asteroid's behavior changes by itself, basically, is what they're...
Can it, right? And yeah, and in the process change its orbit.
Yeah. So some of the ways that their orbits change naturally are being perturbed by Jupiter's gravity. So Jupiter is the most massive planet in the solar system, and so most of the asteroids are between Mars and Jupiter, and Jupiter can give them a nudge every once in a while that pushes them into a new orbit. Also, the absorption and re-radiation of light can create an extra boost of momentum. That's something we call the Yarkovsky effect. It can also change its rotational state so that they rotate either faster or slower. That's called the Yorp effect. And also collision. So asteroids bump into each other every once in a while, and then they can be set up on a new orbit. Sometimes those collisions create many new smaller asteroids, depending on how energetic the collision is too.
Awesome. Does the mass of an asteroid need to be known before sending a satellite to collide and change its orbit?
We would like to know the mass really well. That's probably one of the most important physical parameters to ensure a successful deflection. But depending on the scenario, we might not have that luxury where we have a good mass measurement. We might have a decent a magnitude measurement from the telescopes on Earth. And from the magnitude, you can guesstimate how big, if you make some assumptions about how reflective it is, we call the albedo, so how much light it reflects. But then you're not going to know its density ahead of time. So even if you have a okay volume or diameter estimate, you won't necessarily know what its bulk density is. So asteroids, they're mostly pretty low density. A lot of them, because they're so collisionally processed, they have a lot of void space inside of them. So they might have densities near a gram per cc or just above that. So that's like the density of water, or a little bit higher than water. Something like Bennu is just not that much higher density than water, actually. And then there's others that could have densities that are closer to the full grain density of the meteorites that we're familiar with on Earth. So that would be closer to 2 grams per cc or 2.7 grams per cc. And then there's metal asteroids too. So ahead of time, you might not know the mass, but that's part of what we work on in our group, is actually propagating the uncertainties in the physical properties of asteroids to understand what is the possible range and responses to a given deflection mission, whether it's kinetic or nuclear, and being able to provide really risk-informed assessments to a decision maker, because we're definitely not going to have all the information we want, but we need to be able to make a good decision based on what we do know.
Awesome. So here's another question from one of our young viewers who's 7. How do asteroids get so fast since they just broke off a planet?
Oh yeah, that's a good question. So the they haven't just broken off a planet. They've typically been where they are in space for quite some time, you know, billions of years. They're moving fast in relation to the Earth because everything in space is moving pretty fast. So right now, as we sit here on Earth, we're moving very fast as we're in orbit around the sun, but we can't sense it, we can't feel it because we're not accelerating, we're staying at the same velocity. And asteroid orbits, when they intersect with the Earth's orbit, the difference in velocities is typically significant. And and on top of that, anything that comes towards the Earth, the slowest it can possibly going, unless it's, you know, you're landing a spacecraft and you're using a lot of energy to slow yourself down purposefully. Anything that ballistically comes in, so it's just coming in without any forces, extra forces applied to it, has to come in at least 11 kilometers per second, because that's the escape velocity of Earth. So if you were to throw a ball up at 11 kilometers per second, that's how fast it has to go to escape Earth. And anything coming in, you think of the ball coming the exact reverse direction, by the time it gets to the Earth, because of Earth's gravity, it's going to have accelerated to 11 kilometers per second. So everything that hits us hits at least that fast. And depending on its orbit, it might hit a lot faster. I think the average impact velocity for asteroids at Earth is somewhere around 20 kilometers per second.
Wow, I think we have just a moment or two left for a few last questions here before we run out of time. If any sort of explosion occurs, would there be a wave that would shift the Earth?
Sorry, can you say that one more time?
Sure. If there was an explosion, would it create a wave that shifts the Earth?
Okay, so depending on what was meant by the question, an explosion from an asteroid that's coming into Earth's atmosphere would not shift the Earth. That would not be enough energy to move Earth on its orbit. But if they're asking a question about an explosion from the nuclear deflection technique, that this is a common misunderstanding, is that if we deployed that technique, it would be very, very far from the Earth. It'd be on astronomical length scales, so that that explosion would not affect the Earth in any way whatsoever. And so it's hard for us to visualize or think about as humans on Earth, because we think in human length scales, but on the length scales at which things exist in the solar system and at which we would deflect something, it's so far from the Earth, it would have really literally no effects on us here at Earth if we were to use that technology.
Great. And getting some more comments here. Yes, that telescope behind me here, we search for asteroids. We do real research at Chabot Space and Science Center as well. Shout out to all of our watching astronomers. I think that's all the time that we have for questions. Thank you so much. We really enjoyed your presentation tonight. And I think we have a couple of announcements for our up and coming events. Tomorrow, come back 7 o'clock tomorrow. We'll be talking about the lunar landing sites past and future with Mr. Brian Day, Deputy Staff Scientist at NASA's Solar System Exploration Research Virtual Institute. That's at 7. And tomorrow is International Observe the Moon Night with our live telescope viewing. So don't miss it. Coming up next week, Live Science returns, and next Friday night we'll be back for our monthly family hike, and the subject is bats. So tune in, same channel tomorrow. And thank you so much for participating tonight.
Thank you.
Thanks. Have a good night.